All right, good morning, everyone, and welcome back to Math 115. So today we are going to be talking did I even start 2.5 in the notes? I'm not even sure. I don't even think I got to the end of 2.4. So what we're going to do is, I guess, just finish 2.4. I'm not sure why I put 2.5 here. We're going to finish 2.4. So, if we have a little extra time, we might go back and do another long division example or two. But I just want to remind you of two homeworks which I have posted, which are going to be due on Thursday. Okay, so that's not tomorrow, but the day after tomorrow at 11:59 p.m. is homework 2.3 and homework 2.4a. And then 2.4b homework will be due sometime after that. Okay, I don't want the black pencil since I'm on the blackboard. So 2.4b coming soon. That'll probably be due, I don't know, Friday, or depending on if I finish 2.4 today. Your next assessment is quiz 4, which is going to be today, and that covers sections 1.6 to 2.2, so we'll do that in the last 15 minutes of class. While I remember, I better set myself an alarm so I don't forget.
You could forget.
I could forget, yeah.
Did you notice a difference in the scores when we did it earlier in the class and later? I think better.
No, not really. I didn't. We end at 9:45, right? So I'll set an alarm for 9:28. That'll be when I... Well, I want 2 minutes to be able to pass out the quizzes, and then 15 minutes for you to take the thing. Okay. So, what was I saying again? Oh yeah, I didn't notice a big difference in the grades. That wouldn't be explained by the fact that we were just getting into more complicated material.
Yeah.
So, yeah, I didn't notice anything that had to do with taking it at the start of class. Okay, so that's your next assessment. Your next assessment is going to be exam 2, which is going to be after fall break. Okay, so the Wednesday after fall break is going to be your second exam. It's going to cover a lot of sections, like a lot of sections. It's going to be 1.4 to 1.9, 2.1 to 2.6, and then whatever we get into of chapter 3 before that time, which should be at least like 2 or 3 sections. So I put a 3.x here because I don't know how far we're going to get. I have office hours this week. First office hours are today from 2:30 to 4 in cont 439. Can I have a show of hands on who's planning on coming to office hours today? Okay, I'm just seeing like a couple of hands raised, so we're going to have them in my office. And if too many people show up, then we'll move down to a classroom. So today we will be in cont 439 until otherwise specified. And if I do otherwise specify, I will make sure to post a sticky note on my door, and I will send an email to the class. Okay, so if you can't make it to office hours, but you still want help with homework or whatever, then go to the Tutoring Center in cont on the first floor. You don't need to sign up. You don't need to do anything. You just need to put your body in that room and say, I want to learn math, and they will help you. Okay. Any administrative questions before we start in on content for today? Okay, doesn't seem like there's any hands, so let me remind you what we talked about last time. So last time, did we have something to finish in the previous chapter? No. Last time we talked about rational functions, which what are rational functions? They are quotients of polynomials. By quotient, I mean fraction. So we take one polynomial on top and one polynomial on the bottom, and we call that a rational function because it is a ratio of polynomials. So that's why we call it a rational function. So the top has degree n typically, and the bottom has degree m. Okay, those are just random letters that we choose, but the degree could be different, right? We could have a degree 3 on top and a degree 2 on bottom, or vice versa, or something like that. And the one thing we need to worry about with the domain of rational functions is that the domain should exclude any values that make the denominator 0, right? So if you factor the denominator and you find all of the zeros of that denominator, you need to exclude all of those zeros from the domain of the function for obvious reasons. Namely, we can't divide by 0. Okay, so vertical asymptotes were when we had a vertical line and our function basically blows up near it. Okay, so as x approaches a from the left or as x approaches a from the right, the value of the function approaches infinity or minus infinity. So that looks like something like this. Okay, we're going up, 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 up. Okay, it's a little confusing because we also have, because on these drawings we also have a horizontal asymptote. So let me change the drawing to be more vertical asymptote exclusive. You could have something like this, right? So there's no horizontal asymptote because these guys aren't getting closer and closer to a horizontal line, but they are getting closer and closer to a vertical line as we get close to the value x equals a, okay, or something like that. All right, so that's vertical asymptotes. So when do we have a vertical asymptote? We have a vertical asymptote when x equals a is a 0 of d of x, which is also to say that x minus a is a factor of d of x, the denominator function. That's why I use the letter d for denominator. Okay, so that's about vertical asymptotes. And we have horizontal asymptotes when, okay, notice x is no longer going to a, x is going to infinity. It's the function value that's getting close to a number, okay? So vertical asymptote, we have limit as x goes to a number, we have the function value is going to infinity. In a horizontal asymptote, we have the x values going to infinity and the function value is approaching a number. Okay, so those look like these. As you go really far out to the right or really far out to the left, you are getting very, very close to a certain height. Okay. So those were horizontal asymptotes. And then we talked about graphing 1 over x and transformations of 1 over x. So we just remembered that, well, 1 over x is one of our celebrity functions. So if I want to graph it, I know exactly how to graph it. It looks like this yellow thing here. Yes? It looks like this yellow thing. So if I want to graph -2 over x plus 1, I just view it as, well, it's going to be the graph of 1 over x, but I'm going to move it to the left one. I'm going to vertically stretch it by 2, and I'm going to have a reflection about the x-axis, okay? Those were coming from the +1 and the 2 and the negative sign here. So that was how we graphed that one. And then we had a more complicated one where we saw, well, this weird-looking function, and we thought initially that that doesn't seem like a transformation of 1 over x. It doesn't seem like a transformation of 1 over x because I shouldn't have an x in the numerator and the denominator. This function is not something like 1 over x, right? But we saw if we used long division, we ended up with an equivalent function, the function 3 plus 1 over x minus 1, which is a transformation of 1 over x. It's the graph of 1 over x, but we shift to the right 1 because we're subtracting on the inside, and we shift up 3 because we're adding on the outside. Okay, so that's a special case where in certain circumstances you can graph a rational expression by viewing it as a transformation of the celebrity function 1 over x. So that was where we stopped last time. Are there any questions on what we talked about last time? Okay, doesn't seem like it. So let's talk about something new. And by the way, I just want to encourage that, while we're having class here, if you get confused by something in the notes, I do ask, please do ask a question about it, because I guarantee you that if you are confused about something, then at least one other person in the class is confused about that same thing. It's not a waste of class time to talk about it. interrupt me at will. I beg you. Okay, so with that being said, let's start in on new content for today. So let's talk about when the function n of x over d of x is going to have a vertical asymptote. Well, I sort of lied to you before when I said that, well, I didn't lie to you, but I withheld, okay, I lied by omission, right? I withheld some information, okay, to prove my point. But I'm going to fix my statement now by saying the following. So if the numerator and the denominator, okay, are divided by one another, we get this rational function, and it is going to have a vertical asymptote at x equals a when the denominator becomes 0, right? That's what I said before. But there's a little bit of a caveat, because it is possible also that the numerator has a 0 at the same x value. And if that happens, we're going to see different behavior. So we say r of x has a vertical asymptote at x equals a if a is a 0 of d and it's not a 0 of the numerator. Then we will definitely have a vertical asymptote. Okay, so let's see an example of a vertical asymptote and where we're not going to have a vertical asymptote. So what would we do when we want to start looking at the function f of x equals x squared minus 4? Well, the first thing we would do is to factor the numerator and the denominator. The denominator is already factored, but we can factor the numerator as x minus 2 and x plus 2, yes? Over x plus 3. And we see, aha, I can tell that negative 3 is an asymptote for this function because negative 3 is a 0 of the denominator and it's not a 0 of the numerator, because the only zeros of the numerator are 2 and minus 2. The zeros of the denominator are negative 3. There's none in common, so I can guarantee that we're going to have an asymptote at x equals negative 3. So let me draw in. Here's x equals negative 3. And now let's draw the picture. So so we can determine easily whether we're going to have a blow-up like this or a blow-up like this by just checking what is the sign of this guy to the right, very close to the right of our asymptote. Well, if I plug in something like 3.01, I want to plug in x equals negative 2.99, something like that. Then I'm going to get negative 4.99 on the top times negative 0.99, yeah? And then on the bottom, what will I get? I'll get positive 0.01, yes? So the numerator is becoming a positive number, and the denominator is positive and very small. So, should my graph look like this or like this? Option 1 or option 2? Someone give me the answer and also justify your answer.
1.
Okay, Griffin says 1. Can you tell me why 1 and not 2?
Because it's a big positive number.
Exactly. This number is what we get when we plug in negative 2.99, which is the x value seen like at this dot here on the x-axis, yes? So that dot there on the x-axis, that's x equals negative 2.99. When we plug that in, what do we get? We get a massively large positive number. We're definitely not going to see behavior 2 here, okay? We're going to see something like this. Okay, actually it's probably going to end up looking like that. Okay, so on the left-hand side, what do we have? If I plug in negative 3.01, then this number is not really going to change by much. This number is not going to change by much, but this number is going to not be negative 0.01. It's going to be something like, if I were to plug in x equals negative 3.01, then that would have the effect of inserting a negative sign here, which is going to make our number very big and negative. Okay? Very big and negative. But we'll talk more about how to draw these pictures a little while later. So we definitely have a vertical asymptote on this one. Let's see what happens on the other one. Well, on the other one, we can factor again, right? What does the top become? X plus 3 times x minus 3 divided by x plus 3. Which means, what can we do? We can cancel one of the factors, right? So this becomes x minus 3, provided that what? Is there any condition on this cancellation here? Yeah, provided that x is not negative 3. Why? Because the domain of G is all real numbers except for negative 3, because negative 3 is a 0 of the denominator. So, as long as x is not negative 3, say if it's 4 or something like that, then this would be 4 plus 3, which is 7, and this would be 4 plus 3, and we could cancel them, right? When can we not cancel them? We can't cancel them when it's like 0 over 0. That's a big no-no. We're not in a situation where we can cancel there. So we need to remember that negative 3 is not in the domain. Okay, but for every other value of x, the value of the function should be x minus 3, which, what kind of graph is the function x minus 3? It's a line with slope 1 and y-intercept negative 3, right? So it looks like this. Except, there's one thing that I did wrong when I drew this graph. And that is that when x is negative 3, I put a point on the graph, right? But that's a problem because we said that the x value negative 3 is not in the domain of the function. So we should not have a point on the graph of the function, which has the form negative 3 comma f of negative 3, or g of negative 3, excuse me, because g of negative 3 is not defined, right? G of negative 3 is not defined. So we should not have this point on the graph. So how do we fix that? Well, all we do is we do a little circle to show that that point is not on the graph. Okay, so, I think that a lot of students get confused about these types of drawings because they're like, well, what is with this circle? But I think what you need to do is, in order to understand why we should have a circle here, I think it's important to have a good grasp of what is the domain of a function, right? The domain of a function is the allowable inputs, right? And the graph of the function is the set of points whose x value is the input and whose y value is the output, right? So you have to kind of connect like 3 or 4 concepts in order to understand why we make these kinds of pictures here. But loosely speaking, the denominator can never be negative 3, right? The denominator can never be negative 3 in this fraction. So even though we simplified it, we still have the history of where this came from. This originally was a fraction. So I can't just cancel everything and say, oh, everything's okay, right? Okay, so hopefully that makes some amount of sense of why we put this hole here. Any questions on this before we move on to the next topic? All right. So let's talk about horizontal asymptotes. So far what we said was, what is a horizontal asymptote? We said we have a horizontal asymptote if limit as x goes to infinity of f of x equals k, where k is some number in the reals, right? K is a real number. This is what we've said so far. What we have not said anything about is what is going to cause us to have a horizontal asymptote, which is what we're going to now discuss. Okay? So, here's what I want to say. We have a rational function, okay? A rational function has a horizontal asymptote, at a given y value. So y equals k is going to be a line, right? What kind of line is it going to be? Yeah, it's going to be a horizontal line, right? Because horizontal lines are defined by their height. Vertical lines are defined by their x value. Yes? Okay, so if we have the function, which is a rational function, then I'm going to write it like this. Okay, why do I write it like this? I write it like this to show you that, okay, the top is one polynomial. It has degree something, n, say. And the bottom is another polynomial with different coefficients and possibly different degree, m. Okay? So the degree of the numerator is n, the degree of the denominator is m. And depending on which one is bigger, say if we had like x to the 5th versus x to the 4th, right? Then n would be bigger than m because, okay, let me do a strict example. For example, if we had x to the 6th plus 4 over x to the 5th minus 3, then the degree of the numerator, n, would be what? Yeah, but it should be 6, yeah, is what I was going for. And then, yes, it is larger than the degree of the denominator, which is 5. So therefore, which one of these things is going to be true? Well, it's going to be the first one, right? N is larger than m. Okay, so this is just an example to help you understand what all of this nonsense means. Okay, it's a bunch of letters, isn't it? But all it is it's saying we have a number times x to the something plus another number times x to the something, da-da-da-da-da-da. And then on the denominator, we have the same thing, but with possibly different numbers and possibly different powers. But all we care about for the horizontal asymptote is the leading term of each of these. So we're going to forget all about the rest. We're just going to look at the leading term. Okay, so in this case, we compare just x to the 6th and x to the 5th. I don't care about the 4 or the 3. Okay, so let's talk about what happens when n is larger than m. Well, when the numerator has a bigger power, then roughly speaking, as x becomes really large, this numerator's leading term is going to outweigh the leading term of the denominator, right? Because it'll be much larger when we take it to a larger power, yes? So if n is larger than m, we are going to have no asymptotes, no horizontal asymptotes. If n is equal to m, then we're talking about something like 5x to the 6th over 4x to the 6th, right? And then plus something da-da-da, plus something da-da-da. But all we care about is this. And if we look at a term which looks like this, what would we do? We would cancel out the x to the 6's, and what would we be left with? Just the leading coefficients as a fraction. So if we have something like degree of the numerator is the same as the degree of the denominator, well, when x gets really big, by the leading term test, we know that all of this stuff is not going to mean jack, right? All that we're going to care about is this, and they have the same power of x. So we can cancel that power of x, and what would we be left with? We would be left with the number an over bn. Sorry. Well, I guess it would be n, because they're both the same, right? Is a horizontal asymptote. Okay, then let's talk about what happens when the degree of the numerator is smaller than the degree of the denominator. Well, if the degree of the denominator is bigger, then when x gets really big, the leading term of the denominator is going to be much, much larger than the leading term of the numerator. If you have a number which is like a small number divided by a big number, and the number on bottom is just getting bigger and bigger and bigger and bigger, well, what do we expect this fractional number to become. If the denominator goes to infinity and the numerator is not growing very fast, then we're getting really small, right? Smaller and smaller and smaller and smaller, which means y equals 0 is a horizontal asymptote. Okay? All right, so these are the three options for horizontal asymptotes. One of these three things is going to be true. Okay, one of these three things is going to be true. Any questions on that? All right, let's do an example then. So here we have a rational function, okay, 3x squared minus 1 divided by x plus 2. And our task is just to find all vertical and horizontal asymptotes. So I'm not just doing the horizontal, I'm not just doing the vertical, I'm doing both. So we're going to walk through this example, and then we're going to have some partner work where you get to try some on your own. But first, let me show you how I would walk through this problem. So the first thing that I would do would probably be to factor the numerator, okay? How would I do that? Well, I could rewrite this as 3 times x squared minus 1/3 divided by x plus 2, which I could then rewrite as 3 times, I can think of this as a difference of squares, x plus the square root of 1/3, and then x minus the square root of 1/3. All divided by x plus 2. And now I'm in good shape to tell where are the vertical asymptotes. So why did I need to factor the top in order to find the vertical asymptotes? Can't I just say, well, I know that -2 would make the denominator 0, so it's a vertical asymptote? Or is there any hang-up that I need to also consider here? Exactly. We saw that example where if we have a 0 in the denominator, it doesn't necessarily mean that we're going to have an asymptote. We just saw that if the 0 is in the denominator and in the numerator, then we end up with a hole. So if I want to find all of the vertical asymptotes for this function, I say, well, -2 is probably a candidate. Right? It's probably a candidate. But I also need to make sure that the numerator is not 0 when x is -2. And I can see that it won't be because none of these terms will be 0, right? If I plug in -2 here as well, you'd get what? 12 minus 1. That's not 0. So -2 is a 0 of the denominator, is a 0 of d of x, the denominator, and x equals -2 is not a 0 of the numerator. These two things together mean x equals -2 is a vertical asymptote. Questions so far? We found the vertical asymptote. Right, and I know that I'm not going to have any other vertical asymptotes, right? Because that's the only thing that would make the denominator 0. So that's the only one I need to list. Okay, so I'm happy about that. Now let's see about the horizontal asymptotes. Let me add a page. Now let's see about the horizontal asymptotes. Well, we have r of x equals 3x squared minus 1 divided by x plus 2. So n, which is the degree of the numerator is equal to what? 2, right? Biggest power of x in the numerator. M, which is the degree of the denominator, is 1, right? There's a 1 here, power of 1. So, therefore, n has what relationship with m? What goes in the middle? N is larger than m. So all I'm going to do is I'm going to take this information and I'm going to go back to my little table. What does the table say? If n is larger than m, what am I going to have? No horizontal asymptotes. So, no horizontal asymptotes. And let me just show you really quickly why that's true using Desmos. I'm going to turn that off for a second and do another one. So let's take a look at the difference between the function x squared and the function x cubed and the function x cubed divided by, no, I want it, x cubed divided by x squared. So, what is the deal with these? Okay, what is causing this? So, this is the rational expression. This is the numerator, and this is the denominator. So, what is causing this expression to not have a horizontal asymptote is, roughly speaking, the blue curve as we go to infinity. Okay, remember, we're going really far out to the right, so it's kind of hard to see on this scale. But you can see that the blue curve is growing much, much faster than the red curve is growing. So if we take the ratio of the height of the blue curve divided by the height of the red curve, since the blue curve is growing so much faster than the red curve, the ratio of their heights ultimately, as we go to infinity, is going to never stop growing. Okay? Is that clear? Whereas, if we take a look at something a little bit different, we could take a look at something like x squared, x cubed being the numerator, and what if we made the denominator x cubed plus 25. Okay, x cubed plus 25. Okay, let's see what would happen here. Come on. So we want x cubed and then plus 25. So what's happening here? Well, we have two cubic functions, right? We have two cubic functions. You can see initially they're 25 units apart, because this one's x cubed plus 25. But what happens as we move forward? As we move forward, what happens to the distance between the red curve and the blue curve? Well, the distance between the red curve and the blue curve, they get closer and closer together, right? The heights get closer, yeah? As we move to the right. Which means that the ratio is getting close to what? Basically, we only care about the leading terms here, so the ratio is getting close to 1 as we go far ahead, okay? The ratio is getting close to 1. You can see that, right? So that's why we have a horizontal asymptote of, which is going to be the ratio of the leading coefficients in the case of equal powers. Okay. So that's what I want to say about this problem so far. So what did we do? We found all the vertical asymptotes by checking the zeros of the numerator and denominator. All the zeros of the denominator, which are not a zero of the numerator, will be vertical asymptotes. Then, for horizontal asymptotes, what do we care about? Just the leading terms of the numerator and denominator, and we check which one has a bigger power. Or, if their power is equal, then we compare the coefficients. So, any questions on these examples which we've shown so far? Okay, then let's go ahead and work with a partner for a little while now. So what I'd like you to do is basically replicate this process for two different polynomials, or not polynomials, two different rational expressions. So I'd like you to find all vertical and all horizontal asymptotes if they exist. Obviously, if they exist. If any exist. Spoiler alert, they do. Okay, so go ahead and work on that with a partner. I'll be floating around to help anyone that has some questions. Yeah, but you could do that. So you could use long division on the first one in order to rewrite it as a transformation. Yeah, you could do that. That's one option, but it's not necessary to answer the question. But it would maybe help you. Right, so I mean, it's already fractals, right? Because it's a linear. So we're trying to find, we're trying to get vertical now. So when we have a vertical, right? Yeah, so what's going to make the bar? I would just say. So is the model. Yeah, but it's a specific number, right? There's a specific number that I've plugged in with that, and 1 minus 3x would be equal to 0. 1 will have minus. First thing you do right now is, well, what do we want to do? That's right, 1 minus 3x. That's the denominator. What do we want it to be equal to? Equals 0. Now you know how to find out what x is?
Yeah, I would get
So if you plug in 1/3, multiply by 3, you get 1, right? And 1 minus 1. that's a 0 in the denominator. Are we going to have a vertical asymptote if we have a 0 in the denominator every time? Not every time. We also need to check to make sure that it's not a 0 over 0. It should be a 0 in the denominator and not a 0 in the denominator. So what do we need to check this? We need to check is 5 times 1/3 plus 2 equal to 0. So check this. Plus 2. Plus 3 right.
No, I got dropped first round.
So altogether we get. So is that 0? No. So the numerator is not 0. The denominator is 0. So we have a vertical. You know how to start this long way horizontal asymptotes? Alright, we go help those students. So yeah. Does anyone need a little help? Okay. Does anyone still need like a little more time to work? Okay, take about 30 more seconds here, and then we'll talk these over as a class.
How many questions are on the quiz?
I guess 4 if you want to count it like that, or 2 with 2 parts each.
How do you fit so many sections?
Into what?
And how do you fit like so many sections?
Well, those there's not going to be a question on every section. It's those are what the quiz covers, and I will pull 2 questions basically at random from some of those sections. Does that make sense?
I hope it's got these flashcards. I made them.
That's
You
good.
told me to make them and I made them.
That's good. They won't let you down. Okay, let's come together as a class and discuss, because I think there's quite a bit of meat on these ones. So, or there's quite a bit of vegan supplemental meat on them if you want. Okay, so let's take a look at this. We have r of x is equal to 5x plus 2 over 1 minus 3x. It's a linear function divided by another linear function. So let's talk about the vertical asymptotes first. So to find vertical asymptotes, what are we going to do? We're going to check when is the denominator 0. To do that, I can try to factor this and find the zeros using the zero product property, but it's already factored. All I have to do is set it equal to 0. 1 minus 3x equals 0, therefore 3x equals 1, therefore x equals 1/3. Great, I have a vertical asymptote at 1/3, right? No, we also need to check one other thing. What is that other thing we need to check? We need to check the top and make sure that even though 1/3 is a 0 of the denominator, we need to make sure it is not a 0 of the numerator. So n of 1/3, that's the numerator where we plug in 1/3, would be 5 times 1/3 plus 2, which would be 11/3, which is clearly not 0. Therefore, x equals 1/3 is a vertical asymptote. Great. Now, that's the vertical asymptotes, right? Because there's no other numbers which could make this 0. So, let's now do the horizontal. Well, what is n here? The degree of the numerator. Well, the numerator is a polynomial. What's its degree? 1, right? The degree of a linear polynomial is just 1. The biggest power of x is 1. How about the denominator? Also 1. So therefore, n is equal to m. Which means that y equals to what is going to be a horizontal asymptote? an divided by bn, where these are the coefficients attached to the highest power of x. So what should the top one be? 5. And how about the bottom one? Negative 3. Good. Is a horizontal asymptote. Easy peasy, right? Okay, good. Then let's talk about the second one. Second one is, I think, a lot more tricky. So, our goal is to find any vertical asymptotes if they exist. So let's try. Vertical asymptotes, what am I going to do? I'm going to take the denominator and set it equal to 0. Uh-oh. What's going on here? Could someone explain for me what's going on here? Why am I in a bit of trouble here?
Because you'd have to square negative.
Exactly. Think about it this way. If you move negative 1 to the other side, can you take a number squared and get negative 1 using real numbers? No. So what does that mean? Should I just give up? Yeah? No, I shouldn't give up. I should say, well, I know that anytime the denominator is 0 and the numerator is not 0, I will have a vertical asymptote. I know that the denominator is never 0. What can I then conclude? There is no vertical asymptote, right? Okay, good. So no vertical asymptotes. Interesting. Now let's look at the horizontal asymptotes. Well, the degree of the numerator, n, is what? 1. And how about m, the degree of the denominator? 2. So, n is less than m, right? Let's go back to our table. What did it say? It said, when n is less than m, y equals 0 is a horizontal asymptote. So therefore, y equals 0 is a horizontal asymptote. You can see easily just by looking at the fraction. The denominator is gonna, think about when x is really, 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 really big. If x is like 1,000,000, the top is like 2,000,000. But the bottom is like 1,000,000 squared and 1. Right? 1,000,000 squared is like, I don't know, like 10 to the 12 would be like a sextillion or something like that. Some like crazy big number, right? Yeah, because 1,000 million would be a billion. So we're talking about like, yeah, a stupidly big number. So the denominator is going to be so much bigger than the numerator. So you can tell that this number is going to 0 because the denominator gets really big a lot faster than the numerator does. So we end up with something like a small number divided by a big number. That gets closer and closer to 0. Okay, so any questions on either of these two partner work problems? Either the vertical asymptote part or the horizontal asymptote part for either? Okay, then let's talk about... Damn, I'm going so slow. Okay. All right. Not slow. I'm going the right speed. I just feel like there's too much stuff for me to cover. Okay, so let's talk about the behavior of a rational function near a zero. Okay, so we want to understand... This is about understanding when I make these drawings, basically. Okay, when I make... sorry, not near a zero. Zero is something else. Let's talk about zero. So let's talk about... Okay, what are going to be the zeros of a rational function? Well, if this side is 0, okay, if this side is 0, and the right-hand side is a fraction, what type of fractions are equal to 0? It's the type of fractions where the numerator is 0, right? That's when the entire fraction will be 0. So, if we can rewrite r of x in factored form, where we just factor out one of the zeros from the numerator. Okay, so let's say x equals a is a 0 of the numerator, but not a 0 of the denominator. Right? Then we could rewrite this in the following way. We could rewrite this as s of x divided by d of x times x minus a to the m. Okay, then near x equals a, the value of the rational expression is going to be similar. This means approximately equal to a number a times the function x minus a to the m, right? Which is just x to the m shifted right a units, yeah? X to the m shifted right a units. Okay, so you generally know that x squared, x to the 4th, x to the 6th, they all look like parabolas, right? And then x cubed, x to the 7th, x to the whatever odd power, they look like this. Or if they're negative, they look like this, right? Okay, so you know generally the shape of x to the x minus a to the m. And then you just multiply by a constant. That's nothing but a vertical stretch or shrink. Okay, so what is the number a which we're going to multiply by? It's going to be what we get when we plug the number a into this constant here. When we plug the number a into this constant. So let's see an example. What is the behavior of this rational function going to be? Behavior near x equals 2. Well, basically we need to find out what a is. A is going to be s of a divided by d of a, which in this case is, this is our s, and this is our d. So s of a is going to be, when we plug in 2, we get 4 plus 1 is 9. When we plug in 2 to the denominator, we get 1 times x minus 2 squared. So what I'm getting at here is when we draw the graph of r of x, okay, near x equals 2, we know that the function value is going to be 0 at 2. And so I want to know, well, what does it look like nearby? Well, nearby, it looks like the function 9 times x minus 2 squared, which is just a parabola opening up, stretched by a factor of 9. So nearby, it's going to look something like this. So you can imagine later on we're going to find out all the behavior of the function near all the other zeros, and we're also going to find all of the asymptotes and stuff like that, and then we're going to be able to make a complete picture of what a rational function looks like by connecting all the dots. Okay, so that's where we're going. So we'll stop there for today. It's time for the quiz. Please clear your desks.